This is a tutorial giving an introduction to the Tetracorder system. The Tetracorder system is designed to analyze remote sensing and laboratory spectra used in mapping the Earth and other planets. It could be used for other purposes, but this is the main goal of the system as it's been implemented. The system includes multiple programs on the order of 100,000 lines of code. The spectrum processing routine, SpecPR, is a tool for analyzing individual spectra. It has many core subroutines that are used for the other systems, including Tetracorder. The radiative transfer routines use the Hepke radiative transfer model plus extensions to include sub-wavelength particles, embedded particles, and embedded mixtures, and better solutions for the Chandrasekhar H functions. Tetracorder has a public version and version 4.1 that is available on the USGS websites for the spectroscopy lab. And the newer versions, starting with 5.15, are research versions. We're currently on version 5.26, and that's what will be the emphasis in this tutorial and this follow-on tutorials for what we do commanding-wise. The Tetracorder 5.26 or a slightly later version will be released to the public with the EMIT project. The EMIT is an imaging spectrometer scheduled for launch to the space station on May 1 of 2022. The system also needs support software, post-analysis Tetracorder using the DaVinci program from Arizona State U. There's versions of Tetracorder that run on Windows, but we're not going to emphasize that here because so much has been developed post the Windows compile. So while Tetracorder itself can compile on Windows, the post-processing to synthesize all the results into a state that's more easily viewed by the user running Tetracorder. The Windows just can't cut it. We need the diversity of what can be done on Unix and Linux. Macs run Unix, so all of this can be run on Macs. The system is a combination of C, Fortran, Rat4, DaVinci, and shell scripts. So first, some principles of spectroscopy. So spectral features are an expression of the interaction of light with the chemical bonds. Multiple elements and scattering effects create confusion for accurate mapping with imaging spectroscopy. This includes the strength of absorption bands and how they relate to abundance. As grain size changes, the scattering changes within a particulate surface, creating different spectral signatures. Elemental substitutions shift absorption bands. There are different kinds of mixtures, linear mixtures where you have patches of two different compounds separated on the ground, like in a checkerboard pattern, where light and dark squares on a checkerboard. The light that hits those different patches don't interact between the two squares. Same with like a patch of snow sitting in a field. The snow, if it's thick enough, it will not interact, or the photons will not interact with light from the ground. The nonlinear mixture types are intimate mixtures, which are basically all rocks and soils are mixtures of different mineral grains. We have molecular mixes. For example, a gasoline spill on soil would be more a molecular mix because the gasoline gets in and just coats all the grains. and in the scattering environment, you can't tell a difference between that and a complete molecular mix. There are conditions where different chemical bonds occur, but for the most part, at the resolutions that we typically use with imaging spectroscopy tools that we have available today, we don't see those effects. And then there are coatings, for example, desert varnish on rocks. So the problem with all of this is it creates confusion until you understand it. When you understand it, then you can use it to your advantage and derive quite intimate details of the surface. For example, with grain size differences and the changing shapes of absorption bands, you can derive the grain size of that one compound independent of how much is there. So the other issue is there are tiny differences in the spectral features that are key to distinguishing between compounds and not just the overall spectral shape. So all of this goes into the strategy of how we command tetracorder, and what I describe here in the succeeding slides. This is the way we've decided to do it. It's not necessarily the only way or the best way. We found that it's a pretty effective way to do this mapping strategy, but we're always open to suggestions and refinements to make things better. Another point is spectral channels in a spectrometer are not independent variables. An imaging spectrometer with just a couple of hundred bands can be used to map hundreds and even thousands of compounds. We need to understand the spectral diversity of compounds to identify and map them accurately. So to do this, we need spectral libraries that show that diversity. There's currently no way to independently compute those. There's idea in the remote sensing community about reducing dimensionality of a complex data set. But it's the smallest spectral features that distinguish many compounds. So if you reduce dimensionality too much, you might actually reduce the ability to distinguish between some compounds. So yeah, complications. If it's complicated and we don't understand it, it's a detriment. But if we can understand it, it's a strength. And you can read the slide here. Spectroscopy is certainly complex. We know a lot more than we did 4 decades ago, 4+ decades ago when I was in grad school. But we still have a lot to learn, and I'm sure as instruments get better and our knowledge gets better and our spectral libraries get better, we'll be able to do a lot more than we can today. So I've talked already about grain size effects, bandwidth changes, band saturation, which happens with changing grain size. We can determine grain size remotely using these properties. Absorption features shift with chemistry. That enables us to do chemistry and subtle changes in chemistry remotely. Phase transitions, more band shifts. Thus we can determine phase, solid, liquid, and gas. So all of these complications add up to strengths once we understand them. So Tetracorder is a system for applying algorithms to a single spectrum or a group of spectra, like in an imaging spectrometer dataset. The goal is to identify and map chemistry. Tetracorder is different from other systems because it applies algorithms, and you can choose different algorithms to apply to different problems, and it's used to identify the features that are expressed in spectra and translate those signatures to materials and specific chemistry. The difference here is in a typical remote sensing algorithm, say a band ratio or a principal components analysis, the result is an indicator of something, but it may be indicating one of multiple things. Tetracorder, however, tries to explore all of those different possibilities and make a decision of what the correct answer is. And depending on the specifics of the absorption features, how diagnostic those features are, will give us more confidence in that answer. So some things we may get an answer, but it's not indicative of a very specific um, chemistry. And a good example of this is Fe2 plus absorptions in minerals. Some of them are very common, even though there's some very different chemistry and composition of the mineral. So depending on uh, the exact nature of the absorption band and how diagnostic it is, we need to be aware of how we uh, call out that answer and how robust it is. So in some cases, you'll see Tetracorder putting out things generic Fe2 plus, and so we know there's an Fe2 plus absorption there, but we can't assign it to a very specific mineral. In other cases, we can. As of 2016, so now this is late 2021, so we now have about 35 years of development into Tetracorder with a team of spectroscopists. Most of this work was originally done at the USGS through 2014, and I still work with colleagues at the USGS who have been contributing. So and now PSI is contributing also. And as more people in the community pick up and learn how to command Tetracorder and provide more reference spectra, we can move this further ahead. So Tetracorder analysis is controlled by an expert system. This is different than an AI system, where an AI system uh, learns on its own. An expert system is commanded by experts, in this case, spectroscopy experts who know how to do this commanding and understand the spectrum. The goal is the same expert system can be applied anywhere in the solar system. And we have been applying this for a number of years, a single expert system. There are situations where you may want a custom expert system for a particular problem. For example, mapping oil spills on the Earth does not need to map minerals found in an arid region, for example, where the oil spill is on ocean. So we've applied Tetracorder on all kinds of situations, from um, toxic waste, including acid mine drainage, oil spills, um, disasters like the World Trade Center disaster, to mapping minerals on Moon, Mars, or ice in Saturn's rings. While the same expert system can be used with any spectral range and resolution, sometimes we have done custom things, like the example was the oil on water. But for most applications, for example, minerals on the Earth can also be found on the Moon and Mars, and potentially in Saturn's rings. And Saturn's rings are mostly ice, and ice is on the Earth too. So there's a lot of commonality throughout the solar system. Tetracorder mapping results are automatically analyzed and color-coded as of Tetracorder 5.15 in 2015, and that those post Tetracorder mapping results and color coding has been refined since then. Tetracorder results can be fed to other systems. For example, we have been feeding Tetracorder results on the Carnegie Mellon Zoe rover. So it analyzes the Tetracorder results real time to make decisions on where it's going to drive to next. So one of the goals is real-time mapping of materials with uh, robotic spacecraft or rovers. And not only is it now possible, we've now achieved that in 2021 with the Tetracorder running on the rover. Next would be ideal if we could get an imaging spectrometer on the rover. Then the rover could do mapping real time rather than a profile with the single point spectrometer we have currently. Ideally, the data will flow from the sensor to the analysis screens showing results. This is now possible and is effectively going to be done with the EMET space station system, where data from the space station will come down, will be calibrated, the atmosphere removed, and Tetracorder will be run on the resulting calibrated data at the Jet Propulsion Laboratory, and analysts can see the results pretty quickly, limited only by the compute time of the systems and the transmit time from the spacecraft to ground. So this analysis method and the flow of data from the spectrometer is independent of the spectrometer, so that the same expert system will run on the imaging spectrometer data on the EMET instrument on the space station to the ASD spectrometer that's on the Zoe rover, or any other spectrometer. And any wavelength region is in theory possible. The analysis system now adapts to varying conditions. So if one instrument has one spectral range and another instrument has a different spectral range, the system will adapt and analyze for the features that it can analyze within a given spectral range. Varying atmospheric conditions can throw off calibration, and how we command that is an open science question, but is certainly possible to do with the current system. So we're striving for location independent analysis. That means that the same expert system is used everywhere in the solar system, and we get consistent results on all bodies and all geologic environments. And we've partially achieved that. There's still unknowns that we need more reference spectra. We need to understand things that interfere. For example, we put in mapping prehnite on Mars, and we found that on the Earth, when there's a chlorite or serpentine with some dry vegetation in the same pixel, it can give a signature that looks similar to prehnite. So that adds a complication for Earth, because of the different spectral features produce something similar to something on another planet, even though they're not the same composition. It's a limitation of spectroscopy. So we have to be aware of what the limits of reflectance spectroscopy are. One of the biggest issues in analyzing spectrometer data is the calibration. If the calibration isn't good, it can distort spectral features, and that can give you wrong answers. JPL now has atmospheric correction, which circa 2015 and being refined even to this day, is producing very, very good results for the Earth. The CRISM team has produced very good corrections for Mars spectrometer data, CRISM spectrometer data. So as we get the calibration refined, the Tetracorder results should be better also. Sensor spectral range and gaps, we've mitigated that in the Tetracorder 5 series. Before that, you kind of had to do a custom expert system for each spectral range and different spectral gaps. Spectral resolution, as AVRIS or as the imaging spectrometers get higher spectral resolution, we can distinguish more cases. We've learned that 10 nanometer full width half max is barely adequate. It does a good job, but some things are difficult to distinguish. Data artifacts can cause problems with identification if there are channels deleted due to, say, a hot pixel or something in the spectrometer. That can affect your ability to detect certain conditions, and sometimes that can cause data artifacts. But the algorithm that is used in Tetracorder is reasonably noise tolerant, and we've done a lot of work on that, and Clark et al. 2003, and references therein describe that. Swayze et al. 2003. Methods change due to different sensors due to above. That was a problem pre Tetracorder 5 where you had to adapt the expert system. That's now mitigated, but if the spectral resolution is high enough, it works pretty well. As spectral resolution drops, you may need to still do a custom expert system. But fortunately, most spectrometers are currently in this spectral range, so I think we're in good shape moving forward. I've discussed a lot of this so far. We have better calibrated data. We have to always be on our toes that the calibration is good. We have better atmospheric removals. We have better registration, so we can produce maps easier. We have improved expert system. There's some new features that still need to be explored and fitted in where needed, and that is a curved continuum spectral feature analysis, which will give us fewer false positive detections of trace compounds. This is particularly important in the 3 micron region where spectra are typically curved due to small amounts of water or even large amounts of water in a spectrum or in the surface that is in the spectra when we're trying to map organics that are superimposed on those water absorptions. We have new automated assembly of color map products. The problem with Tetracorder is it puts out so many answers, it literally thousands of files, and trying to go through those to see what you mapped can be challenging. So the new automated assembly of color map products greatly improves that. We can define more color map products pretty easily. We also have a new automated extraction of spectra for each map material. It enables verification, and when something unusual is found, you can see that in the spectra and see the average spectrum quickly rather than having to go hunt it down yourself. And of course, faster computers have helped. So here's an example of Tetracorder 5. It was a mosaic of average data, and this is an automated product from Tetracorder. Now, in the color scene here was the automation, and we defined by a script which minerals went into this map, and then we had to make the key. So the key is put on the to the actual color map output, so you can review these pretty quickly. An interesting thing to note here is you don't see any scene boundaries, and that's because even though there are lighting changes across the track, and there's many flight lines here in this scene, the continuum removed boundaries remove the changing intensities to give just the absorption band strengths. Another one of the products is the vegetation green red edge shift position, and this is using a different algorithm just to illustrate other algorithms can be used to do other things than just simply a feature analysis. And if you have a favorite algorithm that you like to apply for a specific problem, we can drop that into Tetracorder and use it to map whatever that algorithm is supposed to produce. The same Tetracorder expert system that was used for the Salton Sea is here used for Mars CRISM data. And again, more Mars CRISM data. So a lot of remote sensing programs that try and search for materials usually do simple things. They often do just a linear unmixing, and that isn't always appropriate because the real world is more complex. Tetracorder, however, can use all of these conditions, and including molecular mixtures. We just need reference spectra that are representative of what those mixtures look like. And same with coatings. For example, we have hematite coatings on rocks, so we can map a hematite coating. And of course, we have lots of intimate mixtures, and we've constructed linear mixtures to try and bound the problem. I think most people here understand what the rich data that imaging spectroscopy delivers. So this is a quick sequence I'll run through to show the different effects. So this is a semi-natural color image of Cuprite, Nevada with Avarice data. This is Highway 95 running up. Goldfield is just north of the top of the scene. So broadband sensors can see things, but you don't always know what they are, and there's often multiple things can cause the same color. Like the reds here can be caused by multiple minerals, and even just simply the right amount of water in the soil. So the previous slide showed band ratios. This is TM band ratios to show, and it does a pretty effective job at showing differences. You just don't always know what they are. And here's an example of why band ratios are kind of limited. Say you wanted to identify people. So one way would be to measure the total height versus the shoulder height. And here's 4 different images of people, and it shows the height ratio is very similar to all of them, even though the people are different. When we zoom in, we see that even though the distance has changed between the 2 images of myself, the height over shoulder height is the same, but we really can't use this kind of parameter for a person. And if a person crouches down or something, the H over S value changes. So identifying people by ratios of things like this just doesn't work. And that's the same with mineral spectroscopy. You can take a ratio of 2 wavelengths, reflectance at 2 wavelengths, and it might tell you something, but it's not a unique identification. If you want to identify people, just like if you want to identify minerals, you need to be a little more sophisticated. So for example, you can do facial characteristics, and that helps. That gets it a little closer. And imaging spectroscopy is similar. You get diagnostic absorption bands, and you get the shape of those absorption bands, just like the shape of a person's face and so on. So spectral features in a spectrum are used to identify the components in the spectrum. We do that by isolating the feature using continuum removal, and then we do a feature analysis. And the feature analysis in many cases is independent of mixture type. And it's also very computationally simple. And I'll give examples of this. So here's spectral feature analysis. So you can think of your favorite spectral region and features that you see in your favorite spectral region. We just need to know what you as an expert spectroscopist knows are the most key features in the spectrum that you use to identify a compound. And we can put that into Tetracorder and do that same thing. And I've seen people describe how they identify particular things in a spectrum, and it's kind of similar throughout the whole spectrum, whether it's UV to mid-IR, far IR. So here we have the red line is a spectrum from the Cuprite Avarice dataset, and then here are 3 reference spectra, jarosite, hematite, and goethite. And then you can see that even just visually, if you have any spectroscopy training, or maybe even without, you see dips. You see other dips like this one here. these are where the atmosphere is opaque, so we don't get a lot of information. So we've defined what in the reference spectra features continuum to isolate a feature. So this jarosite, you know, if you were a lab spectroscopist only, you might draw the continuum from this point over to this point, or maybe over to this point. But if you drew it to this point, it's in the middle of a terrestrial water band, and it doesn't work. So we've designed the continuum positions to be independent of other interfering things that are common in remotely sensed spectra, whether it's Earth, Mars, or other planets. Fortunately, on other places like the moon, there are no atmospheric features, but there may be other mineral features that you want to avoid confusion with. So note here that the continuum for the jarosite is different than the continuum for the hematite, is different than the continuum for the goethite. And that's important. Also, the jarosite only has one feature, the hematite and the goethite have two. Then in the other wavelength region, we have this feature here at 2.2 microns, and we have a number of different minerals that we're comparing to. So we do the we ratio out the continuum, throw out the stuff outside the continuum, and then compare features. So this is what Tetracorder does. It has removed the continuum for these two features in goethite and fits and does the same continua to the unknown, the average spectrum, and same here. Notice that the red line has different continuum points for each reference material. So the continuum must be removed in the unknown for every reference spectrum. That adds computation, but is necessary. So these are the fit numbers, the correlation coefficients to the least squares fit. We include the continuum endpoints, and that's why some of these are going up above. We've done studies to show that that helps in determining the fit. So the overall fit, there are two absorption bands here, and we use the area of the continuum removed reference spectrum as a weighting to weight these two and come up with a weighted fit. So 0.575 for goethite, 0.97 for hematite, and 0.57 for jarosite. So the best fit in these three cases are hematite. The spectrum Tetracorder would call that pixel containing hematite. It'll do the same thing for another wavelength region, and we call the different wavelength regions groups. So here you see again the continuum is varying with the different minerals, and we see the fit, and we find that the fit is kaolinite KGA-2, which is a well-crystallized kaolinite. This is halloysite is a kaolinite group mineral, but has slightly different absorption bands, as you can see. So in this case, the pixel would be found using two groups, would be found as hematite plus well-crystallized kaolinite. We do that for every pixel in a scene, and then we can produce maps. So here's a evolution of strategies for mapping. And the idea here is we're at a hydrothermal system, Cuprite, Nevada, and we want to find the well-crystallized kaolinite. So early on, if you only had albedo, like a single wavelength, you'd get something like this, and you can't tell where the kaolinite is or not. If we had TM and two broadbands, we could do a ratio of band 5 divided by band 7, and you see something like this. And again, you can't tell where the kaolinite is. Then imaging spectroscopy came along, and people thought, oh, we can do two narrow absorptions or two close wavelengths and better discriminate whether there's an absorption there or not. And we get this. It's not much different than the TM. That was surprising to some. Next would be do a 3-point band depth, and so draw a continuum and measure the distance from the band center to the continuum, and you get this. Again, it didn't do as well as we thought. It, here it's a little brighter in the hydrothermal zone, but lots of false positives outside of it. And it's the same here. A little brighter in the hydrothermal zone, but lots of false positives outside of it. And that's because there are many minerals that have absorptions around 2.2 microns, and alunite is another example. So it'll give a similar response. And you can see these two, even though they're two different minerals, give similar response. So the key then is you can't just do these simple analyses. You have to do the fitting to make sure that what you're fitting is um, this or that. And so if you just do a single mineral, like throw the kaolinite absorption and map for that, and this is what in ENVI, the program SAM, Spectral Angle Mapper, does something like this, something similar. You get something like this. It isolated and reduced some of the false positives, but there's still many, many, many false positives. Tetracorder, however, does that fit to the kaolinite plus the alunite plus dozens of other minerals to find which one it matches, including mixtures between kaolinite and alunite and other minerals. And then we find these are the pixels with the best well-crystallized kaolinite signatures. So orders of magnitude fewer false positives. We do that for many minerals, and then we can produce maps of many different kinds of minerals as shown here and here. Okay, each spectral region is sensitive to different processes in the reflected solar range, or also the emitted thermal emission range in the mid and far IR. So this just lists some of those different regions, and in Tetracorder we split these regions up, and I'll get into those splittings in future tutorials. So, but this gives an indication of some of the different regions that we see, and we split the 1 to 1.3 region up into a number of different subregions. And the 2 to 2.5 micron region is one of our key ranges, but so are, as we get more and more data in these other wavelength regions, we're finding they're very diagnostic also. So Tetracorder can do, we just need to recompile and increase. I'll check the number of groups that we have currently, and a group is a spectral range, and currently it's about 22, I think it is, something like that. And in each spectral range, we can get an answer of the dominant spectral feature, which includes mixtures. So if we have 22 spectral ranges, and each range can have 1, 2, 3, 4 different compounds detected, we can potentially map hundreds of compounds per spectrum. Continuum removal is very important because as different processes work to change the slope and shape of the spectrum, it shifts absorption bands. But removing the continuum restores the feature minimum and the feature shape. So for example, you can almost barely see a feature here, but when we remove it, it's here and it looks exactly like curve A. So that's an important step in the identification process, is defining the continuum, and we need to define it so it isn't interfered with other compounds that may be present. So with Tetracorder, we define 2 ranges for a linear continuum and 2 more, one out here and one down here, if we want to do a curved, and then a cubic spline is fit to the 4 points to do a curved continuum. So how big this range is here depends on the strategy and what's interfering. For example, here it looks like for this spectrum, you could go shorter up this way because this is nice linear, you'd get more data, but going shorter, you're getting into the closer to 2 microns where CO2 bands in the atmosphere, which probably aren't fully corrected, they're difficult to correct, might interfere with an accurate continuum determination. And on this side, you see we're dropping into another absorption band, so we don't want to go too far this way. But we want to go make this large enough that we average 2 or hopefully 3 points, if higher resolution spectrometer, maybe 4 or 5 points, to better define what the continuum is, to reduce noise in determining where the continuum is. So there's a lot of strategies to learn, and we learn that by experimenting with different spectrometers and their various signal to noise and different conditions that we encounter. So once we get the continuum and remove the continuum, we derive the band depth with this equation. In a curved continuum, if we use a straight line, we'll get a false positive. So if there, for example, between these two, here there is a little feature in here on another curved continuum. So we'd see a little bit stronger, but this will still give a false positive. Conversely, if we were the other way, we might get a false negative. You know, we wouldn't see anything there, but unless the feature was stronger. But with a curved continuum, we can get these less false positives, false negatives in the curvature to a much lower level. Another strategy that we use is shoulderness. Shoulderness was needed to distinguish some feature shapes, in particular chlorites and serpentines which have absorption bands in the 2.3 micron region, which is a MgOH combination band, versus organic compounds, which is a CH stretch combination band. But they have different shapes typically, and the following describes what we would have with shoulderness. So shoulderness is a parameter that can be used to distinguish between compounds, and as well, you know, the band depth is still computed, but also this shape of the band. And to illustrate the difference here, see, some of these have a more checkmark shape than others. And if you're drawing a continuum from there to there versus here to here, you'd get a different shape. And we use that, and it has proven very effective in distinguishing organics from minerals in this 2.2, 2.3 micron region. There are many processes from many minerals and a lot of overlapping absorption bands. So deriving a strategy isn't always simple. So when we add a new mineral to the Tetracorder expert system, we do need to run tests on knowns, and we have several known locations where we have imaging spectroscopy data sets where we've done a lot of field work and know what's there. You know, you never know 100%, but you know enough to, if something weird starts showing up. And an example was prehnite showing up in areas where there were chloride serpentines plus dry vegetation. That was an obvious one that came about. Another case that we've seen is where we would see one area where we'd get excellent fit and high response, and another area with the same mineralogy where it would be uniformly lower fit. And when we investigated, we'd find that it's typically a small wavelength shift because the chemistry had changed a little bit. And then knowing that chemistry change, we can then go get that compound with that chemistry, measure the spectrum, and add that to the reference spectra, and then be able to map finer details in chemistry. And here's an example of pyroxenes where the absorption bands shift position, and with that position you can map the chemistry of the pyroxenes or muscovites. And this is a case where we actually discovered this by seeing the problem with how muscovites were mapping in the cuprite area early in the imaging spectroscopy era, and we saw the band shifts, and now change. We map the composition of the muscovites quite nicely, and we map the position of the pyroxenes, and we even produce color maps of the pyroxene band position, so you can see the different pyroxene compositions. This can be done for the Moon, Mars, and Earth, where pyroxenes are exposed. um, Important for climate change effects and dust are hematite grain sizes, and we do that by mapping the um, uh, the width of absorption bands, and that we're doing pretty well. We've got now have SEM photos of our reference spectra, so we know the grain sizes, so we're getting better calibrations in what these different grain sizes mean when we see the different spectral signatures. We have a lot of intimate mixtures in the reference spectra, and we can certainly use more. So people are certainly encouraged to contribute. Um, the problem with linear versus nonlinear mixture is in a intimate mixture, the projected surface area of the grains in the mixture dominates, and the darkest particle at a given wavelength dominates. So you have competing things that make make the mixtures quite complex. But fortunately, the absorption bands pretty much stay the same. You know, at the extreme ends, they can change shape a little bit, but the main effects are the reflectance level. And a good example is here, where we see montmorillonite plus charcoal, and as the amount of charcoal increases, the reflectance decreases and the band strength decreases. But when we remove the continuum, the feature shapes are pretty much the same. Same with keeping the grain sizes constant, the abundance constant, and changing the grain size. We see changes in reflectance level and changes in band depth, but the absorption bands stay the same shape, and we can identify montmorillonite in all of these spectra. Organic compounds are certainly sought after on other planets, and it's important on the Earth too for mapping compounds, whether it's um, an oil spill, for example, or mapping different types of vegetation. So organics are all over the place, and we need to map those pretty well. So we can do that in the 3.3 to 3.5 micron region, as well as a 1.7 and 2.3 micron region. Each region has a different sensitivity. At 3 to 3.5 microns, we have the highest sensitivity for parts per thousand and maybe less abundances. There are many, many types of organics with different bonding, and we can see what those bondings are. The spectra have some similarities on a coarse scale, but when you get down to the fine details, you can tell them apart. You can see here, for example, this band is at this position here, and the bands are shifting in position with different compositions. And then single bond, double bond, and triple bond, the fundamentals shift position, and then that translates into shifting at other wavelengths too. We have in Tetracorder currently a number of um, organic compounds. We have reference spectra for many more, and just need time to add add more in. Organics are used to make a lot of materials on Earth. So while At the longer wavelengths, we can see the CH bands. In the visible, we see a lot of different coloring agents. So while the color may look different, we can tell what something is by the longer wavelength band. So all of these bands out here are pretty much in common, saying nylon, even though the visible has spectra all over the place. This high peak here and this one here are due to fluorescent compounds added to the nylon. Plants have a lot of diversity too. We see the cellulose and lignin absorptions out here at the longer wavelengths in woods and plant products, but in the visible, again, we see different spectral shapes, including dyes that fluoresce to make different colors. Similar, more plant and wood products. Plants can also be identified by species, and here's an example of that. The problem with plants is they change with time, so you need to have reference spectra for each part of the growing season, and we currently don't have that. At least we don't have it in Tetracorder. An example of mapping vegetation species, and here we had 97% accuracy. You can map biota of all kinds of types. There's so a lot has been done in this area, and the spectra look quite different depending on the species. So different bacteria show different spectral signatures and have different colors. The UV should be rich in spectral features depending on the light source. You can also get all kinds of emission bands with organics, and those features can extend into the UV. There's also absorptions that go into the UV. So the Earth's atmosphere cuts off quite a lot by 0.3 microns, but on other planets we can get down to 0.2 and even down to 0.1 microns. Minerals also show a lot of diversity. These all need to, this UV stuff needs to be programmed into Tetracorder to identify these materials. We currently don't have that in Tetracorder. Sulfides too show different spectral features in the UV. Some of these will be difficult, like is it just a slope, or do you map on this feature here, and how do you map that, and how robust is that identification? And that's something we need to learn and understand. Again, more spectral features in the UV, and how do we command the expert system? For example, a continuum from here to here would show this spectral feature at 0.32 microns. And is that a unique identification of kaolinite? I don't know. Some things are just scattering effects. So like this upturn in this meteorite is due to submicron particles creating Me or Rayleigh scattering, creating the bluing. And how we attack that strategy is a question, but we can certainly do it. Some things will absorb, so the things like tholins and irons and other metals, carbon black in fine grains, just absorb with a continuum into the UV. And how do we describe that? So that's to be determined how we would analyze for that in Tetracorder. Another example, here's water ice with embedded Rayleigh absorbers, in this case nano iron, and when the iron grains are embedded in the ice grains, and the same with silicates, you get an absorption. But if the iron grains are outside the host grains, then you get increased scattering and a bluing effect. So we've had a number of breakthroughs um, in the 2015 plus with Tetracorder 1.5 up to the current um, 5.26. We've added in a lot of 1.9 micron region water absorptions, and it appears loosely diagnostic of mineralogy. There's a lot of overlapping bands. So, but for example, the sulfates tend to be at longer wavelengths than say the water and clay minerals. So we can do more type, not specific mineralogy, but at least families of different minerals. We need to understand how that would, how a soil with varied mineralogy would affect the band position. A sulfate-rich soil should show different band position than, say, just a clay-rich soil, and I have seen that. We now have, as I mentioned before, we have products. So every mineral that is mapped in an imaging spectrometer, there's a gray image produced that is auto-stretched, and where that mineral was mapped is put on top of that gray image in red pixels. So you can see for any individual mineral what maps where. And then those mineral maps are put together into colored maps for a more overview product. And all of these are auto-generated. Otherwise, it would take weeks for one person with tools like Envy or others to assemble all of these by hand. The Tetracorder 5.15 does multiple spectral regions, as I've discussed, and over 500 reference spectra. That's grown since the 5.15, so I think we're up to maybe 700 or so for 5.26 and growing. As we add more, the runtime increases linearly, whereas some other algorithms, it increases as the square. So we can add a lot more and not have a problem with mapping large data sets. So quickly, the same code currently compiles on Unix, Linux, and Macs. Macs need X Windows installed and needs the compilers, but those are readily available. We have virtually unlimited reference spectra and spectral features. We we just need to recompile and increase the array sizes if we want to go bigger. The Better Expert system that adapts circa 2014 has enabled us to get beyond a lot of the limitations and apply Tetracorder to more different data sets without side effects. So this was a big breakthrough. We need to develop more capabilities. There's a lot of capabilities that are in the Tetracorder Expert system that we haven't fully explored yet, and that needs to be done. We're still running on Spectral Library 06, although with the EMIT project, we found that some spectra needed to be higher quality, so we've gone beyond what's in Spectral Library 07, and we're retrofitting those into the current scheme that uses Spectral Library 06 and a companion research library. So we may just skip over Library 07 together. The system is 64-bit, so we're pretty much unlimited on sizes. It's actually hard to go above 32 765 pixel swath width because image sizes are defined to be smaller than that. So we'd have to change the image formats that are output for all these the reference spectra images with the gray level and so on. So that's a problem, but that's a problem that's not related to the 64-bit architecture. It's a problem with image size standards. So we'll we can work on that, but for the most part, we haven't needed to hit this very often. For the entire moon, I did have to subset the full resolution of the data by just a few percent to make it fit. Okay, let's go through what a typical entry is. So in an expert system. So this is for one reference material. We have the group number. So there's group 1 through n can be anything up to the limit that we define, which I think is currently around 30 or so. Group 0 is a special group. Group 0 is something that is applied to all other groups unless you say don't apply it to a group. So um, just think of this as a group number for any example. You can turn it on and off if you just turn this to no, and then it wouldn't be mapped, but that's a custom change to the expert system. The data, the unknown data are in reflectance. So in theory, which we haven't implemented because we haven't needed to, but this could be emittance, and we could have all the reference spectra for that in emittance. And that shouldn't be hard to turn on, but it currently hasn't been tested. We early on had an idea to convolve the spectra on the fly, but we've abandoned that. I mean, we can turn it back on, but we've abandoned it because we felt that it's better to convolve the spectral libraries so that you have the references available at the resolution of your spectrometer. So when you want to do comparisons, you've got them. Because if we didn't do that, you'd end up having to do it anyway when you make figures for the journal, for scientific papers. In some cases, we do a ratio, and we do that for the vegetation red edge shift. Most cases, we don't. That's a pre-process thing. So that's a special case of a pre-process, and we have other possibilities for pre-processing. This one doesn't need it, and most entries don't need it. The algorithm choice, we call it tricorder because it's after the Star Trek tricorder system. That's the spectral feature fitting routine that does a least squares fit with continuum removed spectral features. The ID for this material, this reference material, is a melting snow. So then you define the library reference spectra. And there are 3 entries for small, medium, and large spectra. Small spectra are up to 2171 channels, and we have never had to go beyond this, so we didn't put in the reference spectrum number. So this is a SpecPR format file, and the SpecPR format file name and the record number where to get the spectrum from. There's an A here and a B here, so you can actually have 2 spectra. So for example, you may have your reference spectrum measured the vis near IR with one spectrometer, and the IR measured with an FTIR spectrometer. You could define the FTIR spectra with a different record number here. In this case, it's the same. Oops, let's go down. Then we define the features. So feature 1 from spectrum A, reference spectrum A versus spectrum B. It's a diagnostic feature, a curved continuum, and the following parameters are in wavelength. So there's 1, 2, 3, 4 pairs of numbers. So these are the continuum interval. So the leftmost continuum interval that describes the curvature relative to the next leftmost continuum interval. Then on the other side of the absorption band minimum, the right continuum and the second right continuum. If this was an uppercase L, you wouldn't have the pink numbers here, you just have the yellow. So you'd have two sets of continuum intervals. Then you have other parameters that can affect whether or not you're going to see this material or not. The continuum threshold, CT continuum threshold, must be between 0.08 and 0.1 on a 0 to 1 reflectance scale. The shoulderness needs to be greater than 0.1 to 0.2, and there's two numbers here because some parameters will work in what's called fuzzy logic. So if the shoulderness is below 0.1, the correlation coefficient that's from this least squares continuum removed analysis is set to 0. If it's above 0.2, that number is multiplied by 1. If it's between 0.1 and 0.2, it's linearly interpreted. So if it was 0.15, then the fit would be multiplied by 0.5. Excuse me, 0.5. This is features that are in the system and haven't been fully explored on how we approach this. But say you had a feature where there was an atmospheric absorption, or commonly another material that had an absorption here, and you want to ignore that in the fit. So this ignores those features, those wavelength regions. We have modes. Mode is all for this case. This again is an experimental idea that we could have something in there custom for Mars orbit or Earth orbit or so on. Ideally, it would be all for everything, and it would be the same mapping for everywhere we do. And currently, that's the way we've done it. We don't have any modes in the expert system at the moment. There's an idea where we should move the continuum point around in case some of the channels in a spectrometer are deleted. So that is in here. Operationally, it can become difficult to know what to do. So how we implement this is for a given spectrum is challenging. But we have that option, and same with the right continuum point. So that's for just one feature. Then you can have multiple features, and so here are a couple of more other features that are defined. Oops, let's see. Then there are also not features. So some materials are identified by seeing one feature but not another feature. For example, distinguishing montmorillonite from a muscovite. The montmorillonite 2.2 band is pretty much identical in both compounds, but muscovites have a second band at 2.3 microns. So in a muscovite or a montmorillonite, we would have a not muscovite feature defined. Then there are other constraints. After all the features and the feature constraints are defined, we have the correlation coefficient must be, fuzzy logic again, greater than 0.7 or it gets reduced. The depth has to be, this is the continuum removed band depth, has to be greater than 0.06 or fuzzy logic, it gets reduced. Band ratios, if you want to do band ratios, that can be done. And then there are temperature constraints. So for example, if you are mapping, say, CO2 ice, it only has a given range that may exist on Mars, but not on the Earth. So if you have the temperature range in there appropriately, then we wouldn't see it on the Earth, but we could find it on Mars. There's similarly pressure constraints. So if for example, liquid water doesn't exist on Mars at the low pressures there, so if for any liquid water entry, we should have a pressure constraint on there. Ideally, we'd make this in the future into a phase diagram, and how to command that needs to be determined. Then the output is what to output. And for each compound, there can be up to three things: the correlation coefficient to the um, to the fitting, and that's a weighted correlation coefficient when you have multiple features. The band depth, and again, that's the weighted band depth for all the features, and the weighted fit times depth. So it's the feature 1 fit times feature 1 depth, feature 2 fit times feature 2 depth, and then put together weighted by the band areas of the reference spectrum. What to call the output? So there would be a snow.melting.1a.fit, snow.melting, so on, .depth, .fd. Then how to scale the output. So this has an 8-bit output, so the images are 8-bit. You can also do 16-bit, where the max value of 255 corresponds to a band depth of 0.5, and the file is compressed with a zip compressor. That's gzip. Then, depending on what is found, if you find this material, you may want to do something else. So this degrades action to case 23. The degrading idea is something we've implemented but haven't explored what it does. And so the idea is, if the fits are getting small and you're trying to do very fine chemistry, maybe you want to not say that that fine chemistry, but get a more general answer that would be a better catch-all in case there is noise. So how we do that is a concept for the future. For single spectra, for example, the Zoe rover, when it's taking spectra in the field, it can announce via a sound file, play that sound file so you can hear what the answer was. So if you're walking around in the field with a spectrometer and the spectrometer is taking data, you don't have to look at the screen. You need to be concentrated on where you're walking so you don't step on a snake or fall off a cliff or something, and the computer can tell you the results via sound. So in conclusion, we all know that spectroscopy can detect a lot of different materials, and with imaging spectroscopy, we have context, geologic context. So the combination of imaging and spectroscopy tells both, delivering orders of magnitude more science than either alone. And with the modern tools that we have today, new and better calibration, imaging spectroscopy analysis enables us to go into a new era in mapping materials, whether on the Earth or throughout the solar system. So it is feasible to map all kinds of water, mineralogy, organics, and signatures of life throughout the solar system with tools like Tetracorder. And we can make this better with more entries into the expert system, and including more ideas from varied experts in spectroscopy and imaging. The illustrations here, this is the Earth. This is Cooperite, Nevada, a 3D view of Tetracorder output. The moon with water and minerals on the moon. The blue is water. Mars, we're mapping on Mars with Chrism, and Enceladus, a moon of Saturn, and Saturn itself. And next up will be an imaging spectrometer going to Jupiter on the Europa mission.